In this video, we will talk about byte and endianness. We know that computers is a world of 0 and 1. So if you look at your computer, you will actually see zeros and ones everywhere. This looks way too subtle, so scientists come up with the notation of byte. At the beginning, the number of bits in a byte was actually hardware dependent. There were 6-bit and 9-bit byte computers in 1960s, and at the time, people often used the term syllable instead of byte as a group of bit streams. Later on in 1990s, people started to use 8-bit byte as a standard, and modern architectures such as Hexadecimal and ARM start to commonly use 8-bit as the smallest building block of storage. To represent a byte, we usually use hexadecimal numbers. For example, suppose we have a byte with bits 1010110. We then split this 8 bits into two groups. The first group is the highest 4 bits, and the second group is the lowest 4 bit. For the highest 4 bits, the value is 10, which we will use A to represent. For the lowest 4 bits, the value is 12. We then use letter C to represent it. We put two hexadecimals together, and we get byte hex AC. Now we know how to represent a byte, the smallest building block in an architecture. Next, let's talk about how to use bytes to represent different types of variables. First, let's take a look at character. Suppose we have a character, A is equal to letter A. How are we going to store letter A in memory? We will first convert letter A to a number, and the way that we convert it is to use ASCII, American Standard Code for Information Interchange. Letter A in ASCII is equal to hex 61. So we store hex 61 in the memory, and we look at it in the binary form, it's going to be 0, 1, 1, 0, 0, 0, 0, 1. From now on, we're going to zoom out a little bit and focus on each byte instead of each bit. And now let's put more characters together. Suppose we have a string with two characters, A followed by B. The ASCII value of A is hex 61, and the ASCII value of B is hex 62. Now we're going to just put them together from the low address to the high memory address. The first byte is going to be hex 61, and the second byte is going to be hex 62. Next, let's talk about integers. Suppose we have an integer I equal to 1,100. So how are we going to store the value 1,100 to memory? We first convert the integer from base 10 to base 16. So we will have I is equal to hex 446. And then we're going to extend this integer to 4 bytes because integer is usually stored as 4 bytes in memory. So we extend it, and we will have I is equal to hex 000004 4C. So now we have the 4 bytes representation for this integer. The question is, how are we going to put this 4 bytes into the 4 bytes allocated in our memory? There are two ways to do it. One is to put 00 to byte 1, 00 to byte 2, 04 to byte 3, and 4C to byte 4. And that way is called big endian, meaning that we're going to put the highest significant byte into the lowest memory address. Another way, which is more commonly used in current architectures such as x86 and ARM, is little endian, which will put the least significant byte to the lowest address. So basically, we're going to flip the order and then put for C, which is the rightmost one. If we look at the digits to the lowest memory address, which is the leftmost one, if you look at the memory from low to high, left to right. And likewise, we're going to put 04 to the second byte, 00 to the third byte, and 00 to the fourth byte. Similarly, if we have a string with characters hex for C, hex for 0, hex 00, and hex 00s, each one represents a byte of this string, how are we going to convert that to an integer? If we look at the memory, we'll see that string is going to store it from the first byte as the first character, and the second byte as the second character, the third byte as the third character, and the fourth byte as the first character. So we're going to have those bytes from low to high memory address. But then when we convert that to an integer, we need to again flip the order. We're going to put 4C as the least significant byte of the integer, and then 04 as the second least, 00 as the third least, and the other 00 as the highest in this integer. In the end, we will get the entire integer equal to hex 446, which is equal to 1000 and 100. This is all about endianness, which we can also call it byte order. Different architecture has different definition of byte order, and in this course, we will be focusing on little endian. Least significant byte goes to lowest memory address. This may not be very easy for you, but that's fine. Usually, we don't really have to touch this by ourselves. We can use existing functions to switch in between. For example, if we want to convert from the integer to the actual byte sequences in the memory, we can use the Python's struct package, and we can use the pack function in package struct. We can just simply call struct.pack with this format string and with the specific number. In the format string, small means the endianness is little endianness, and I means the number that shows followed by the format string is an integer. If we want to convert from a byte sequence to an integer, we can use another function, also in package struct, called unpacked. Function unpacked is composed of two arguments. The first argument is a format string, similar to pack. The small symbol means little endianness, and I means integer. The second argument of unpacked is the string that will be unpacked through this function. And here, because unpacked can actually convert a string to multiple integers or the multiple elements, we're going to refer to the first element that is unpacked from this function, which will be 1000 and 100. For more information regarding function struct.unpacked and the format string, please refer to the Python manual.